Good morning, everyone. Welcome to another episode of Sound Talk Show. We are going to code Wolfram language Mathematica today. So this is what we are going to code. This is a package I wrote about 30 years ago. This is paraplot, enhanced functions for plotting parametric equations for Mathematica. So let me show you some graphics. So for example, you can plot, this is called caustics, basically a ray reflected around from a curve. So this is a parabola, so this is a typical lamp situation. So caustics, so you can see many of the properties. That's what this package do. It just generates these graphics, allows you to plot these graphics for visualization of geometry and for educational purposes. So I wrote this like around 1994 to 1997. And so it's been 30 years basically, or 25. And the last time I updated this package is about 2004 or so. So I'm revisiting this package. It's been 30 years. There's a lot of changes in Wolfram language, and but most of them, vast majority, it still works. You see, so that's some of the graphics. Let me show you. Okay, so if you want to see, this is one of my most popular website, Visual Dictionary of Spatial Plane Curves. It's being linked from university math departments, like from thousands of websites back in 1990, from 1998 to 2008. But basically, Wikipedia took over and other websites since 2010 or so. So all these graphics are done mostly in 1997, and it was cutting edge technology. And today I'm going to update them. So a lot code. Wolfram language has been evolving for 30 years, and so there are some improvements I can make to the package. So for example, here is the source code. Okay, so here's the source code. So this is a file, paraplot.m. You open it. This is a Wolfram language code, or also known as Mathematica. Okay, so so here's the source code. Here's the inline documentation. And let's go down. So here is the code. This is the code for drawing normal lines, and this is and then here's the code for drawing tangent lines. This is a parallel curve, and this is caustics. We have just shown. Here is kind of the code for drawing caustic lines. Caustic meaning reflection of rays like these. So I'm going to update the code. Okay, so this is just gonna be me coding. It's probably boring for you guys. Yeah, am I live? Yeah, I think so. Okay, so I'm just gonna code it. Yeah, so about Wolfram language Mathematica, if you don't know yet, just search for Xia Li Wolfram language or Mathematica, and you can find my tutorials. You go there, Wolfram language Mathematica tutorials, and you can download Wolfram language for free. It began to be free about 4 years ago or 5. So you can download there, and some information. I tell you what they are, what it is about. And from this tutorial, you can learn the complete tutorial for programmers. If you are familiar with JavaScript, Python, C, C++, Java, any of the language, if you are already a programmer, then you can learn for my tutorial from the ground up. And mostly I teach you understand how Wolfram language works, because Wolfram language is a term rewriting system. It's a functional programming language and term rewriting system you likely have never seen in any other language, not in Haskell, not in Lisp. In a way, it's kind of like Lisp macros. So imagine every function you write is Lisp macros. It's kind of like that, okay? So except the Lisp macros is far more advanced. It's symbolic pattern matching. So imagine if you are coding Lisp, every function is defined by a macro, and you have very advanced pattern matching, symbolic matching for macro. That is what kind of it's like in Wolfram language. Okay, so that's an introduction. You can read the tutorial to learn it. So I'm and download it, and I'm going to start to code it. Okay, so this is mostly just for myself. Oh, we have 6 concurrent viewers. So if you are here, say hi. If you have some questions about Wolfram language or Mathematica, ask me, okay? Hello, Zuzribu. Okay, so let's code. So let me tell you what I'm gonna do. Okay, so here is the source code. You can view the source code in Wolfram language. So, so here is how it looks like in Wolfram language. Let's magnify, okay? So here's the documentation, copyright, okay, and here is the inline documentation. Let's go down, 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 go down. So here is starting to have code. This begin is to declare a namespace. So you are starting, I'm starting my own namespace. Basically this is like writing a library in Python or Java. So anyway, documentation. So here's code. So you can see here's code. Okay, so this file is paraplot.m. Okay, so that's this file. And let me just start to code. Let me focus on what I need to do. Then maybe I explain what I'm doing. Okay. So anyway, so this package has been almost like 15 years. I haven't touched it. So so there is quite a few changes, and Wolfram language has added about 1,000 more functions. So actually Wolfram language has added 5,000, something around 5,000 functions since 20 years ago. So there is quite a lot to do, and also in the past 30 years, there's a lot of changes in computing, in the hardware, CPU, GPU, and the style of documentation, the wording. The word is different from 20 years ago, because 20 years ago, you don't even have Wikipedia, and you barely have the internet. So when you need to know mathematics, basically you read textbooks. So it's not like today. Today you have cell phones and everything. So there's Wolfram language has also added a lot of additions and some incompatible changes. So there's a lot to change, reword the documentation and so on. So let me get to what I want to do. Okay, so this file is .mb. Okay, so this is my original source code. Let's see how I want to do this. What I want to do. If I just started to do what I need to do, then you won't understand anything. This is a description of this video. I mean, this is the purpose of today's live stream. I'm just gonna code my stuff. You won't understand a thing. It's just like in a real life programming project at a job. It even takes an hour to explain, to let any outsider to understand what you are doing, because so it's like real life coding. But however, I'm going to try to explain some part of it, so at least you get some sense of what I'm doing, what I need to do. Okay, let's focus. Let me show you. Let's start to load Wolfram language from the ground up. Okay, so there's some bugs I need to fix. For example, let me show you some bugs. Okay, so you can see all these are fine. You can see all these are fine, but however, you see this got a pink background. That means there's some error. So if you click on that, you can see coordinate indeterminate should be a real pair of numbers or a scale of offset form. Basically, you got division by 0. So when you compute this curve is interesting. Okay, it's called cycloid. It's this curve. Anyways, there's quite a lot things to explain. So this curve is called cycloid. Okay, so let me just demo then. So you go to Visual Dictionary of Special Plane Curves, then you go to cycloid. Okay, there it is, cycloid. So this curve is what happens if you draw a circle on a line and you trace out a point on a wheel on the circle. So this is a cycloid, and it's one of the very famous curve about 200 years ago, because this curve is a solution to, imagine if you have a ball and you have a slope, you drop the ball will roll down, right? So obviously, the higher the angle of inclination, the ball will reach to the ground faster. But however, if you make the slope curved, will it reach the ground faster than a straight slope? Or even if so what is the shape of the curve such that if you drop the ball, it will roll down the fastest according by the laws of physics. So it turns out the solution of that slope is this curve called cycloid, and you can generate this curve by rolling a circle. So laws of calculus. This problem belongs to the calculus of variation. So this is interesting part of calculus. Typically, you don't learn that, they don't tell you these interesting things in school. So anyway, so this curve, but then you can generate what's called a, this is the evolute. Yeah, okay, so you can generate the evolute of the curve, and the evolute of a cycloid is itself. So anyway, that's a lot math I won't go into. If you want to read it, you can click here and understand what evolute is about. So there's a visual animation. You can understand what's the evolute. So this animation is showing the evolute of an ellipse. So this red dots traced out is the evolute of a ellipse. Okay, so then the evolute of a cycloid is itself. So for example, this blue curve, the evolute is this red one. It is it itself. Then the evolute of that is again, itself. So that's why, so that's what this code is trying to do. Is trying to illustrate the evolute of a cycloid. Okay. But now it's got error. So you see, we got somewhere in the computation, we got a basically division by 0, like 1/0. So indeterminate. So that's a bug. It wasn't this. I don't have this bug like 20 years ago, but somehow in the current version of Wolfram language, I have that bug. So I need to fix that. Okay, so that's one of the things I need to fix. Let's focus on that. Let's see if I can fix this bug today. That would be the focus of this video. You see the bug happened here again. And there are some other bugs. So for example, this expression, you are supposed to, the result should be like this, okay? This should be the result. It shows the inversion of a hyperbola, okay? This should be the result. But however, if you plot it now, you get this instead. So something is wrong. So basically, these two bugs, I believe these two bugs is what I need to fix, okay? So let's just focus on doing that. Okay, so close that, don't save, and let's start Wolfram language. Close that, don't save, start from the beginning. Okay, launch it. So do you think it's possible to make a game using Wolfram math plots? Yes, of course. Now there are two separate questions. Is it possible to create a game using the ideas of geometry, in particular plotting curves, or more specifically surfaces? When you have surfaces, oh my God, it's pure, it's amazing, okay? Let me talk about that. So it is not just possible, it would be amazing. It would be one of the best seller if you create a 3D game, because I have been wanting to do that for a long time. For like 20 years ago, I was thinking about that. But I don't know how to write a game, despite I tried to learn it. It's very complex, the OpenGL stuff. But so if you create a game with idea of either curves or more specifically, I have in mind 3D surfaces, you are going to have a spectacular 3D game, okay? Like like today's 3D game, you can walk inside it, you can move around. It would be spectacular. I'm gonna show you a few of that, of the idea, okay? So yeah, but we just need someone to write it. But some games, they already employ some of that idea. For example, in Zelda, back in 1999, Zelda 64. Okay, you have this character, Link, that goes through a tunnel. Okay, so Zelda 64 gameplay. Shit. Yeah, this Brave search is no good. So let's go to Google. So let me keep focused. I want to talk about something, okay? So it is certainly fantastic if you create a game with mathematical ideas. Now, however, you are talking about Wolfram language. Can you use Wolfram language to create such a game? Yeah, you can, but like it's no good, okay? You can use Wolfram language in a notebook. You can create a game like Tetris, that sort of thing. But if you want to create a 3D game like the type of games you are familiar with, no, you cannot do that with Wolfram language, and you don't want to do that with Wolfram language, okay? So Wolfram language is not for that. For that you go to C++, things like that. So in Zelda, you have, so you have this Link character, and in this game you have Link go through a tunnel. So you go inside the tunnel, then the tunnel become twisted. It's like, upside down twisting. Then you come out from the tunnel to some other side. So that is a incredible idea, using the idea of three-dimensional curves and surfaces, three-dimensional surfaces, okay? So let me show you. Let me finish talking about that, and let's get back to the Wolfram language code. So for example, here are some of the surfaces, and for example, I want to show you minimal surfaces. Minimal surfaces is most spectacular. Okay, so for example, this let me show you this one. Okay, so for example, this one. Now this is a minimal surface, so it's a three-dimensional surface. So as you can see, it's kind of symmetric, and you got these holes in it. So now imagine the Zelda game or whatever shooter game or whatever. So your character walks inside this hole. So that's an interesting thing about these surfaces, because this surface divides the 3D space into several sections. Now, some of the surfaces, so you have to imagine this surface extends all over. So this is just showing part of it. Now, some of it is periodic. Okay, so let me show you an example. Here's another example. Again, this expands to all the space. So you got this hole. So you see, you got this hole. This hole gets you into this, like a second story. Then you go around. Then you drop into that hole. Gets you to the next floor. So this surface, it's like a screw. It fills the space, so you can go around different floors, kind of. It partitions the 3D space into. In fact, it doesn't partition because, wait, does it? Yes, it does. I think it does. It partitions the space into two spaces separate from each other. You can never go from one space to the other. You see, because this hole, so you look at this hole actually drops you to this floor. But on this floor dropped you to so basically you have even floors and odd floors. You can go from any even floor to another even floor, but you can never reach the odd floors. So this is why it is interesting. So imagine if you are the a character in a 3D game. You cannot get to the other side, you see, unless maybe there's a hole there. So that's that makes it a puzzle. By the way, when you move like a human, you walk around buildings without getting over a bird's eye view of the whole map. In game usually you have a little map. That's kind of like cheating, right? Because in reality, you don't get a map like that unless today you have iPhone. You use you have Google Maps, but in real life, without this map technology, you don't have that. So you don't know which room goes where, like in a puzzle. So let me just show you some pictures to illustrate the idea. So like a labyrinth, right? Without a overview from above, you don't know where you are. So when in that situation, you have to rely on your senses, like when did you turn or leave a thread. So that's called dead reckoning. Okay, that kind of navigation is called dead reckoning. Okay, very interesting. So now imagine, we are familiar with these labyrinth kind of 2D puzzles. But now imagine in a 3D case, you have this, so it's very, it kind of makes the interesting level to the next level. So you have to realize, you have to kind of relying on your senses to determine whether you can get to the other side or how many different sides are there, things like that. So that's another example. There's quite a few. Let me show you, for example, this one. This is called Kasher JE Saddle Tower. Kasher is a German geometer. it's one of the top geometers specializing in minimal surfaces. He taught me a lot mathematics, So in this, so for example, there's also that one. So this kind of surfaces partition the space into weird, compartments. So I think it makes it very interesting. And you have things like that. It's hard to imagine how exactly this expands, but that's one of the, and you have gyroid. And today, with Wikipedia, you have lots of better images, you see. So this is another minimal surface. So you have so many holes. So that's very interesting. Okay, so that's one of the things I've been thinking of doing, but I don't think I'll ever do it because I'm getting old. So we need someone to, game expert to work on this idea. Okay. Yeah. So back to the question: if you're gonna, you can do that, but if can you do that with Mathematica? No. You need to use a game engine. Okay. Or you even need to anyway. So I'm gonna stop there because otherwise it'll be nonstop. So that's about that. So by the way, all these graphics you see here are generated by Wolfram language. I did them like long time ago, 20 years ago. Except some of them are generated by my professor, my friend and mentor, Professor Richard Palais. Many of these, his 3D Explore Math. That's his software. Okay, so anyway, so that's some interesting things about differential geometry, three-dimensional surfaces idea in games. Okay, let's get back, and we talked about Dead Reckoning, Labyrinth, Gyroid, Geometry, okay, Zelda. Let's get back to what I need to do. Okay, so let's start Wolfram language. Let's load it. Okay, so it's started. Now close it. Don't save. Now let's go to the directory and let's open my package. Open it. Okay, so here is my package. Now select all, run it. Okay, so here's all the code and it's done. Okay, now open the examples. Open it. Okay, documentation. Now let's, so for example, let's delete that and run it. Do you want to automatically evaluate all initialization cells? No, because we already loaded. So this is what this package does. It can draw a parametric curve, but using the color variation to show where does the curve begin. So normally, if you do this in Wolfram language, I'm not sure it can do it today, but I don't think so. Parametric plot. Okay, so if you use Wolfram language, you get this. You don't know where's the beginning of the curve, where's the end. So my package adds that enhancement. Okay, so it works. Let's just run another example. Okay, delete that. Do it. Okay. Delete that. Do it. Okay. Now this is also, let's run it. Okay, so each time it generates a different color. Okay, so but I want to yeah, let's get to one of the error problems. So for example, here, delete that, run it, okay? You got an error. Click indeterminate coordinate, okay? So let's fix this. Let's see. Evolute is kind of difficult. So yeah, I think so. How long have I been? 30 minutes. I think I'm just gonna start to code. So evolute. So let's look at my package. Search for evolute. Now I wrote this long time ago, so some of the ideas I don't remember offhand. Okay. Now, where is evolute defined? What? Okay, I don't want. Yeah, okay, so. So anyway, let me see the comment. Sam Hammer, hey. Okay, so what I want to do, so let's see. So all these error, so let's see, so all this error is about indeterminate, basically 1 divided by 0 somewhere. And it happens when you plot evolute. Okay, so what is evolute? Let me try to explain what is evolute. Okay, so the evolute is, okay, so let's go to plane curves. Go down. You have a page explaining evolute. Okay, there. Evolute is basically the center of osculating circle. Okay, so you can see the blue curve is ellipse, and so let me see if I can explain this. Okay, so if you have a curve like that, you know the concept of a tangent, right? So if you have a point on the curve, the line closest to that curve, approximate that curve at that point, is called tangent. So for example, here the tangent line would be here the tangent line would be like that. Okay, so that's called the tangent of a point on a curve. Now, there's another concept similar to that. You see, when you have a curve, you see some points on a curve. At that point, the curve is more curved. For example, if you have a point here, the point there is not too much of a curve. It's rather, there's no curve. But over here, it's very highly curved. So if you have a curve with a sharp turn, you know, then another sharp turn, you see this point is very tight. On the other hand, this point is not so tight, you know, something like that, okay? Tight. So there's a concept of curvature. So the more tight, curvature is basically at any point on the curve, it measures how tight is the curve, how sharp a turn is at that point, okay? So that's called curvature of a curve. And then you can use a circle to approximate that curvature to illustrate. For example, you know, so here this illustration shows that. Now, so at any point on a curve, you can have a circle. This circle is called osculating circle. Osculate means kiss. So it's a kissing circle. In other words, it's a circle that kisses the point on the curve. You know, so if the turning point is very tight, then your osculating circle is very small. When the point is not very tight, then the circle is very large. So this is osculating circle. So on any point on the curve, you have a osculating circle at that point. Then once you have a circle, you have a center of that circle. So the trace of the center of the circle is called the evolute of the given curve. Okay, so again, let me repeat. Given a curve, on any point on the curve, you have a circle called osculating circle associated at that point. And this circle has a center. So of all the centers of the oscillating circle forms another curve. And this new curve is called the evolute of the original curve. Okay, that's the idea. So so we need to dive into the code. I need to, so let's start to dive into the code, shall we? So here, so to do that, it's best to now I know why this happened, because if you add 0.1, then you don't have the error. You see, this one got the error, but this one no error. You got an error because you are starting at 0. When you start at 0, you got this kind of division by 0 thing. So how do you fix that? So this is about evolute. This is about evolute. So I don't even remember my code. Evolutes. Okay, so let's see. So that's a documentation. Then plot evolute is false. So here you are getting the optional value for the evolute. Okay, so let's see. Okay, so far so good. Yes. So the value, the variable is this one, p evolute. Okay, now let's search for that. So what is this part doing? So we have a if expression here. So let's highlight the p-evolute. Okay, so all values of p-evolute becomes yellow. Now here's the if statement. Okay, and if this and these are true, p-evolute equals to that. So if they are all false, so plot evolute, so we can look at for example, here's the documentation for this option, plot evolute. Okay, so evolute of a curve is the locus of its center of curvature, exactly. So given a point on a curve, we need to find the point that is the center of the curvature, okay? So that's what we have to do in order for this code to work. So the p-evolute here is actually just true or false, okay? So that's not exactly what we want. So if it's false, then oh, there it is. So we are trying to compute velocity vector list and acceleration vector list. The velocity vector list is basically derivatives. Then the acceleration vector list is basically second derivatives. So this is about, parametric plot. So if you don't know what parametric plot is, let me show you. Okay, so for example, you say t, let's magnify. Let's say t squared, okay? That basically give you a parabola. So now you say t from 0 to 2. Okay, so you can kind of see a parabola. So this is parametric curve. So basically, parametric curve is defined by two functions. The first function is over here, the second function is there. So x equals to a function, y equals to another function. Then the function's value goes from -2 to 2. So for example, what if the second part is sine t? Then you got a sine curve. Now the interesting, so this is how a plot of a function works. So you have the first part is just x, they don't change. Then the second part is y, a function. That's a normal plot. Now, what's interesting about parametric plot is that you can make the first function change. So for example, let's say t squared and sine t. Let's see what we get, okay? Let's make a copy of that. Let's do it. You see, you got this kind of interesting thing. Let's see what happens if -2 to 20. Okay, so it basically becomes a straight line. I mean, kind of U-shaped. Okay, very interesting. To 10, wow. Wow, very interesting. Yeah, so you can see, let's say, now let's times this by t, what happens? Okay, So let's say -10 to 10. Okay, because the square, let's make it third power. Okay, so that's the fun thing about mathematics. So you can see it gives you all kind of curves. Okay, so that's about parametric plot. So when you want so now if you take the derivative of the first function and take the derivative of the second function, and so you got two new functions, then you evaluate at many values, t equals to -2, -1, and so on. That gives you the velocity at that point, at the time t. And if you take the second derivative, you get the acceleration value at that point, okay? So that's what those means. So what I'm doing here is that, if the user does not request any of these evolute or whatever, then you just set them to empty list, meaning that you don't have to compute them because you don't need it. The purpose is to plot the curve. So if the user doesn't request to plot evolute, you don't need. So, but the user requests that, then you need to compute. So you can see it's over here. So you got velocity vector list. Okay, so velocity, then acceleration. Okay, so let's see. So velocity, let's color it. Okay, pink. Then acceleration, color it green. Okay, so you can see velocity is the first derivative. Okay. Then the acceleration is, so if these features are requested by user, then you compute the acceleration list. Okay, so you take the second derivative. Okay, so we got that. Now we understand. Okay, so this indeterminate error basically came from these two lines. When you have, so let's see, so the evolute, so yeah, okay, so when you have this curve, this cycloid curve, at this cusp point, at this sharp turning point, there is no derivative. So in fact, it's either no derivative or the derivative is infinite, something like that. So that's why we get this error. So let's see. Can you do some fire sales? No, I don't know what that is. Okay. Okay, so we almost got it. So we can see where this error likely came from. I'm pretty sure it came from one of these. Okay, the derivative and second derivative. But okay, so let's think about this. So you see, you avoid the error if you just increment the t a little bit. You avoid, computing at these sharp turning points. So this error is actually inevitable, because this error came from mathematics. I mean, this, the derivative at that point is not defined, basically. You see, the function is this. So if you compute this function starting at 0, what you get? t0. Okay, so you got 0, 0, right? Now let's try it again. Let's do the derivative. Okay, okay, I haven't done calculus for a long time, for like 20 years. So derivative of a function. Okay, let's see how we do this. Okay, so that's the documentation. Now let's read up about I believe that's what you want. Okay, so give the partial derivative of a function with respect to x. Okay, this is what we want. Gives a multiple derivative of that. Okay, so derivative of this thing, two functions, with respect to t, what you get? You get that. Then if you, okay, so then if you replace t by 0, you get 0, 0, 2. Okay, but why does our arrow come up? Where does it come up? Second derivative. Okay, so let's do the second derivative. Oh, wait. You need to say, yeah. T first derivative, second derivative. Okay, exactly. Yeah, so the derivative just becomes sine cosine. The derivative of a constant is 0. That's right. I forgot my calculus. Okay, so back to the code. So you compute the first derivative here. You got 0, 0, okay? Then if you compute a second derivative, you also got 0, 0 for if you start at 0, okay? So the problem is not here because here we simply have a list, this velocity vector list or acceleration vector list that sum of their points is 0, 0. Okay, so that doesn't give you a problem. You start to have a problem when you divide that by 0 or something divided that by that. Okay, so let's go to the next occurrence of velocity vector list. Okay. Okay, velocity. Vector list. Curvature. Okay, curvature is actually one of the more complex thing. Okay, that's it here. So now you need to find this curvature GP. GP stands for graphics primitive. This function is calling it. I think that's where the problem is. So let's search for this function. curvature GP. Yeah, so the function is here. Curvature GP. Now, where is this? Okay, so now I need to look at my documentation. So this code is a bit complex. You can see, God, this is one of the more complex part. So let's see, where is this function? Let's see the documentation I have. Yeah, so here's a code. Find previous, find next, curvature GPS. Oh, I don't have documentation for it. That's rare. Okay, so curvature GPS, basically this function returns a list of graphics primitives like lines and circles. And so it takes these arguments. So a list of points on the curve, a list of velocity vectors of those points, and acceleration vectors. Okay, then circle, evolute, radius. Okay, yeah, some there it is. So square root, first last velocity vector. So here is a problem because this part may become 0. So when this part becomes 0, you got divided by 0. Yeah, so there it is. So let me change. Okay, I think I found a problem. If you just change this, instead of 3 equal sign, change it to 2 equal sign, it'll work. Okay, I think so. If you do that, then this error, let me show you, indeterminate will go away. Okay, let's just try that. So now okay, so where do we change it? Yeah, let's just change it here. Actually, we shouldn't make a backup. And let's just do it. Okay, change triple equal to double equal. Okay, and change this to a approximate 0. Okay, yeah. Okay, now we just evaluate this block of code. Go back here, make a copy of this part and run it. Let's see. Still error. God. Let's make sure. Okay, maybe we need to restart because... Do we need to restart? Yeah, probably. Okay, let's restart. Okay. This is a change we made. Close it. Save. Close it. Don't save. Okay, and here, let's just do quit kernel. Okay, now Open it again. Okay, select all, shift return, rename. Fantastic. Okay, close it, open the example, then go to where that there. Okay, now make a copy of it, run it. No, don't re-evaluate other. We still got error. Okay, so let's try this. Okay, so this is kind of the key here. So if we have uh, 0, 0, would it equal? It equals to true. Triple equal C, that's false. So this is a problem in a field called numerical analysis because it's kind of tricky. I believe this is where the error came from. Because if you can determine, some number is 0, if we know for sure we got a 0 vector, then we simply return 0, 0. We don't do anything. But otherwise, we are trying to compute a normal. Okay, so wait. So here is a normal unit vector. Yeah, we need that. Okay, maybe the problem is here. So here is you are computing the curvature. K is a traditional function name for curvature. And our function for curvature is here. Oh, they are there. So we forgot to change there. The two places we need to change. Okay, so maybe that will fix it. So we need to open this again. Let's just change here, okay? Yeah, so what okay, make a backup first, just to be sure. So you need to change that. Here and here. So you see, the triple equal means whether the structures are symbolically the same, while the double equal in Wolfram language means they are approximately the same. Okay, so there's a difference. The equality sign, there's always big complexity in any language. For example, in Python, in Java, if you have a value that's a list, then when you compare one list is equal to another, you have the issue of whether if you are comparing their reference address, they are equal, or whether their actual component value are equal. So it gets very complex. the determination of equality. That is why in Emac-Lisp you have like 5 different equality tests depending on the type of the value. And similarly for Haskell and type theory, the identity equality is extremely complex. Okay, so those of you who are trolling, not recommended, okay? Return of the loan something, it's when you drink something for $3 and something. Okay, those you guys are trolling, go away, okay? So let's see how do we fix this. Let's just change that, okay? Okay, let's do that. Okay, now we're gonna quit kernel again. Quit local, yes. Then we're gonna open this. Open it. Then select all, evaluate it. Okay, done. Close it. Back here. Try this again. Do it. No. Yeah. Still error. So this error is indeterminate. I believe you get that if you do that. 1 divided by 0. Okay, complex infinity. What if you have okay, let me try something else. Let's see the documentation for if. So if can take a third argument. Now okay, so first argument, second argument. Can take a fourth argument, okay? I believe that's new. So you can see first argument, second argument, third argument. So let's give a fourth argument, 0, okay? And here let's do the same. First argument, second argument, third argument. Wait. 1. Test true, false, vector list. Okay. Test true, false, vector list. Okay, let's try that. Quit kernel again. Quit. close that, open this, select all, evaluate, go back here, run it. No. Same error. It should be just here, map thread. Is there somewhere this happened again? If that, then that. It test true, false. Oh, okay, so yeah, so here, so okay, let's try again. Save it. Permission denied. Okay. Okay, close this. Now save it, open it. Start again, quit the kernel. Okay, select all, evaluate it. Back here, run this. No. Yeah. Okay, yeah, that's something is wrong. Now, where does this occur? Now, last negative, you reverse. Yeah, so you can see here they are reversing the order. So you are given x and y. Now it becomes negative y and x. So x becomes negative y and y becomes x. You are doing that because you are getting a perpendicular vector of the original. And then you divide it by the square root and first that's so that is computing the length of a vector. So in Wolfram language, now they have a function to do that. It wasn't available 20 years ago. Normalized form, no. Yeah, so unit vector, no. You want the norm. So norm computes the length of a vector, okay? So for example, norm 1, 1, 1, okay? So the vector 1, 1, the length is square root of 2. That's correct. So instead of doing that here, now we can just say norm, okay? Yeah, so norm. Okay, that should be the same. That should do it. Now, okay, so let's search for square root. So this happened in quite a few places. It also happens here, so you can just say norm. Okay, so then search again. Norm. Okay. Happens one more place. So this is computing the tangent line. So you also run into this issue. So this issue, let's start to drill down. So the problem is just this function, okay? So let's put it here. Put it here. So this function is giving you this indeterminate error, okay? And we can make it, we can try to simplify it, okay? We still got the problem, you know. So now, in fact, let's just say 2, 1. I believe it still get the problem. Yep. So now, instead of 1 to 60, 1 to just 10 of them, you see, much simpler. Now, let's say 0.25, let's just say 4 of them. You see, we still got this error, but now it's much simpler. Now let's remove the aspect ratio, let's remove the line style. Okay, we still got the problem. Now remove the aspect ratio, so simplify it. Okay, so if you don't plot the evolute, will the error still be there? Let's try it. Run it? No. Okay, so it's only when you plot the evolute this bug happens. So yeah, so the problem is with the evolute somewhere. Yeah, so this evolute, and this evolute, basically the problem is in somewhere in the velocity vector list and acceleration vector list. Okay, so but when you compute the derivative, will the problem occur? No, because you simply get 0. You see, when you compute the derivative of, does it give you divide by 0? No, I don't think so. Yeah, so this is not the source of our problem, but the source of our problem is when you try to do this curvature. Yeah, I'm pretty sure it's when you try to do the curvature. Okay. So here is the curvature call. Oh, okay, so the curvature function, the last argument is a list of true or false. Okay, now let's go to the definition of curvature. GP, okay? So there it is, and here are the parameters. Okay, and so the last 3 elements are, each one of them is true or false. True means plotted. Plot the circle, the osculating circle, and this is the center of the circle, and this is the radius, the line of this to the center. Okay, so then we back to here. Indeterminate, true or false? False. True, that if it's false, then you get that. So why don't we just say that? Okay. So this k is a curvature function. Oh god, the curvature function. Let's just do this again. So if it's true, then 0. Otherwise, that otherwise 0. Test true, false if it's indeterminate, also 0. So when curvature returns 0, what happens? Oh, there it is. Yeah, so here is a problem. So 1 over least. Okay, so there is a problem. Radius least. I found the problem. So you see 1 divided by this curvature function. This curvature function here returns 0 sometimes. So what you're gonna do? So what is this radius least used? Center vectors. Okay, normal unit least times radius least. Yeah, that's a problem. You see, you divide by 0. Yeah, so the problem is here. The problem is here. So 1 divided by 0, you get that sometimes. So what can you do? You cannot simply, so you see this curvature part is a list of values, okay? It's a list of values, and some of them is 0, maybe 0. So what can you do to avoid? So when you 1 divided by this list, you get a list of 1 divided by that. Okay, so how can you fix that? You cannot simply remove those values, elements that are 0. Because if you do that, then you changed the length of this list. And that's no good because the length of this list needs to be used, because if you change the length of the radius list, then that list has a different length than the normal unit vector list. So then that means you cannot multiply them together, element by element. So and same thing for the center points. So center points is the center of the osculating circle. Okay, so and what are we using this for? We are using this for to draw the circle, basically. Yeah. So you see, we draw the circle, and we draw the center of the circle, and then we draw the radius, a line from the point on the curve to the center of the osculating circle. Okay. So in order to draw that, we have these variables, center vectors, center points. Okay, center vector, center points. Okay. So yeah, I kind of know what to do. Almost done fixing the problem. So the problem is some of these elements in this list is 0. You cannot simply delete them. If you want to delete them, you have to delete also the same elements in the normal unit vector list and center vector. Yeah, so you have to delete all of them in one shot, the corresponding elements. Okay, so yeah, I kind of know what to do. So for example, So for example, you have a list something, okay, some of them are 0, and you have another list, let's say x0, x2, x3, x4. Let's say you have another list of several values now, and then you have another list. The important thing is that all these lists have the same number of items. So if you delete the zeros in the first list, you also need to delete the corresponding elements, okay? So what we can do here is okay, so actually the problem is here. You see, the problem is 1 divided by 0. So the problem is that okay, God, I know what is the problem. You see, the curvature. So for example, this would be that would be the that would correspond to this, okay? So now if you have 1 divided by that, you got that. That is the problem. Yeah. So you need to close it. Oh God. Okay, I need to think about this. Okay, I've been sitting for 90 minutes. I need a break. How many people are watching? 1, 2, 3. Okay. Fantastic. Someone is watching. Okay, thank you. So yeah, I'm gonna take a break for 4 minutes and let's come back. We know the problem now. Yeah. So okay, be right back. 1 megaton of coffee. Let me describe the problem. Let's just go slowly. Now, in my normal coding, of course, I wouldn't be talking. Actually, I talk to myself a lot because when you talk or write things down, it helps you clarify the thoughts. The k is a function that computes how do you spell compute? So like this, okay? So let me just do it so people can understand. So k is a function that computes curvature. Then something like this, where some items are 0. So when you 1 over that, then you get the division by 0. That is your problem. You know, you get a value of complex infinity, okay? When 1 divided by 0, you get complex infinity. And then, so our code continues to, to multiply. So when you have a unit vector times 0, then you get a 0, 0. You get a 0 vector. And then, so which is okay, center, which is okay, but actually wrong, because it's no longer center of the osculating circle, center of the the circle of curvature. But anyway, basically when you get a 0, that means at that point on the curve, you do not have a curvature defined. So you cannot have a osculating circle. So that means, so whenever at those points, you don't want to compute anything at those points. Ah, God, so what you gonna do? So what you gonna do here? So this curvature function, so this curvature function, if we change it, you see, the thing is, we don't want to change the length of the list. Okay, so yeah, I think I have to do this offline. So, because this is not so easy to fix. One of the easy way is simply to turn off the warning messages. Nah, that wouldn't work. Actually, I already turned it off, I think. Because you can see Okay, let's see. Search for off. You see, we already, so this line already turns off infinity, turns off errors of infinity. Let's close that. You know, this thing turns off infinity indeterminate. Yeah, but how do you gonna solve this? God. Go back to our problem. So the problem, yeah. Close, yeah. Go to it. Let's just comment here so you can see. And here, let's just make it one line. Single line, Wolfram language. Okay, so yeah, so the problem is this line. How do you solve the problem? You got a list of values. Some of them are 0. The best solution is just to delete those 0 elements, okay? But if you want to do that, you also have to delete the corresponding points of this and that, okay? And can you do that? Yes. So yeah, easy, okay? So velocity vector list. So you compute the radius list first. You compute this thing first. So actually we can start to fix it. So for example, curvature list is a value. We declare it here as another variable. Let's say here, okay? There. Okay, so curvature list, then you can define curvature list here, okay? So there equals to that, okay? So you got a curvature list, then some of the value will be 0, okay? But now you know which elements are problematic. So once you know that, you can shorten the, let's see, you can shorten the velocity vector list. Therefore, your normal vector list will be correct length, right? That's right. Okay, and then so similarly okay, let's move the radius list here. Okay, so similarly your radius list, okay, so I can put it here. So then the center vectors will also be corresponding, correct length. Then center points will be also where does the t-point list come from? Okay, they will not be the correct length. You need to also change the length of t-point list. Okay. So anyway, that's but okay. So you can properly delete some of the zero elements. But however, if you do that, then this curvature graphics primitive function will return a list where the length of the list will not be necessarily the same as the input list of points on the curve. That's not so good because you expect the lengths to always be the same. Let's look at where curvature GPS is called. Okay, so curvature, okay, so basically you see, this is how you generate the lines of radius. This is how you generate you generate the lines of radial lines and the point, these red dots. So in order to generate those graphics, you rely on the curvature graphics primitive. Okay. So now let's look at where are these variables used. Okay. Oh, then delete cases. What? Oh, we already have delete cases. What? Delete cases by what criteria? Okay. What? Did you finish your advance of code already? Have you been watching the videos? If you have, you know the answer. What is your intention of asking that question? Oh God, so this problem, do I want to continue? Yeah, let's continue because let's just, that's the point of this video. So it's going to be boring from the beginning. So anyway, so how do you fix this problem? You got so here is your radial lines, here's radial point, the center of circle points. So this curvature thing, curvature is the problematic thing because you run into the undefined situation where you have a cusp, or in catastrophe theory, they are called singularity. Like today we are approaching singularity. Those points are called singularity, okay? Just for fun, let's chat random. Catastrophe theory, okay? There it is, catastrophe theory. Actually, I don't know the subject too much. But basically, okay, so you have what? Fold catastrophe. Okay, I don't know what that is. But you can see here they are trying to show cusp catastrophe. That's what we got. You see this cusp, these pointed sharp points. That's the cusp catastrophe. In fact, we just plotted a graph of it today. I mean, 2 days ago. Yeah, you see all those points are cusps, sharp points. Why are they why are they catastrophe? Because at those points, things goes wrong. Things goes out of the ordinary. It's like into a black hole. Because every point on a curve, they have properties. They have velocity, they have curvature, they have tangent, they have normal. It's well defined. But when you reach one of these cusp point, everything breaks. You got 1 divided by 0. You don't have velocity. Velocity becomes 0. Curvature is undefined. Things like that. So that's catastrophe. So at those points, that's what this is what I'm gonna show. I'm gonna show it. Okay. So anyway, that's what this catastrophe theory is about. I don't know much about it, but that's the basic idea. They study when the situations, in what circumstances these cusps happen. Okay, so let's read it. Cusp catastrophe. So you have this equation. We can plot it. Let's ramble. Let's ramble a bit and x4 ax2 bx. What is it? X squared. Okay, so ax squared, that's equals to 0, I suppose. And okay, so I believe implicit plot it's contour plot x -3 to 3. Let's say, what is A and B? Fucking stupid. A and B. Let's see. I'm not even sure that works. Let's see. Where is the Y? What? Yeah. X fourth power ax squared plus bx. Oh, a equals to 0, a less than 0. Oh, a is a variable, so a changes. Okay, so you got that kind of situation. Yeah, anyway, yeah, I'm not gonna plot it. So anyway, that's a digression. So how do I solve this problem? I have to, okay, I cannot do it online. I mean, I have to think about it. I cannot just talk and stuff. Yeah. and I'm getting tired. Okay, so what are you doing now? Contour plots. Oh, syntax error, that's why. There it is. So what are they saying? A equals to 2. So what is the Wikipedia saying? The Wikipedia is saying A less than 0. Let's see. So A less than 0, negative 2. You don't get any contours. Why is that? What is this Wikipedia thing? Oh, dvdx. What? They're taking a derivative. Okay, so they have to take the derivative. The cusp geometry is very common when one explores what happens to a fold bifurcation if a second parameter, b, is added to the control space. Okay. Varying the parameters, one finds that there is now a curve, blue, of points in AB space where stability is lost, where the stable solution will suddenly jump to an alternative outcome. Okay, that's catastrophe theory. So hyperbolic umbilic catastrophe, elliptic umbilic catastrophe, parabolic umbilic catastrophe, Arnold's notation, chaos theory. Okay, yeah, they don't say much. Singularity theory. Let's see. What is singularity theory? This article has problems. In math, singularity theory studies spaces that are almost manifolds, but not quite. A string can serve as an example of a one-dimensional manifold if one neglects its thickness. A singularity can be made by balling it up, dropping it on the floor, and flattening it. In some places, the flat string will cross itself in an approximate X shape. The point on the floor where it does this are one kind of singularity. Yeah. Again, cusps and double points and stuff. Okay, so but they really have nothing to do with with debugging our program. Our problem is we got this. Our problem is this. We got this list. So here's our problem. Okay, we got a list of points, and some of them are 0. When that happens, we need to shorten the list. We need to remove those elements. But if we do that, then you see the curvature. So if we do that, then okay, so we just directly, okay, so we can shorten them within this function, no problem. Right. Let's do that. Okay, let's just do that. Fuck. Okay, so let's do that. So here is the function definition, and it's actually quite long, but you guys probably cannot read this, but I can. Okay, but okay, so it's not too long though, but so for example, let me shorten it so you can kind of see what is this. Oh, this is normal. So we are actually just defining. So we are defining the curvature list. We are defining the radius list. We are defining the normal unit list. Okay. Then we are defining the center vectors list. Then we are defining the center point list. Okay. It's also close. And then what's this? Let me shorten the code so you can see what's going on. Yeah, then we are actually generating the graphics. So you see these 3 parts. You see, we are returning this list. This list is a list of 3 things. Okay. Okay, so we are just returning a list of 3 things. Each of those things is a graphics primitive. It's basically a bunch of circles that represents the osculating circles, or a bunch of lines that represents the point on the curve to the center of the circle. Then a bunch of lines, that's the radius. Okay, so what is this evolute? Center point, so T point, so okay. Yeah, I know what to do, but I'm kind of tired here. So again, the main problem is this. Okay, so you can get the positions. Okay, let me show you what that is. Position index that returns the indexes where some criteria occur. So we want to know a list of all indexes where 0 occur. Yeah. So give an association between a unique elements. Okay, that's what not position is what we want. Yeah, position. So So for example, so this curvature list, we want to know all the indexes where 0 occur. So we can just say position, okay, curvature list, then 0, okay? So it tells us it happens at index 2 and index 6, correct? Okay, so once we got the index, we can use this index to remove element by index. So that would be delete okay, I forgot what is that. Let's go to Wolfram tutorial. Okay, list. So you go to the list, then you want to delete element by position. So let's go to list operations. You see, in Wolfram language, you have many ways to delete elements of a list. You can delete by using an index, or you can delete by using a function criteria. If the function returns true, delete those, Or you can delete elements by using pattern matching. Now, this way is not available in most languages. So anyway, so we want, so now, but our problem, we got a list of indexes. We want to delete them, okay? So here, delete element in list, delete by index range. That's not what we want. We don't want the range. We want delete by position. That's what we want, okay? Delete expression n. Then you can have a list of positions. That's what we want, okay? So for example, let's go back to our code. Let me show you how this works. Okay, so for example, let's define this. Let's define, so for example, this is a corresponding T-point list, okay? For example, they have the same number of elements. Now, you get the position of the 0 in curvature list, then you just say delete, what was the function? Just delete. Okay, then you delete the T-points, then you delete by the position of the indexes, that. Okay, run it, you see the corresponding elements are removed. So we can use this methodology to fix our problem, to fix out this. Okay, yeah. So now we know the curvature list, okay? Then so now we need to know the position. 0 indexes. 0 positions. Okay, 0. Let's say. Okay, so there. Okay, there. That's good. Now we created a new variable. Let's add it here. Okay. Module is like Lisp's let. Okay, it's like JavaScript let. Just declare local variables. Okay, so curvature list. Okay, then 0 position list. Okay, fantastic. Then you need to delete. That's right. Delete. New curvature list equals to delete curvature list by the 0 position. Okay, fantastic. Okay, we are coding blindly because I know what, it's in my head. I have the structure. So we don't have to trial and error. Okay, so we got the new curvature list. That's what we want. Then oh God, this is not perfect. This is not good code, but I'm just doing it for the live stream because so that we can get somewhere. Because in real life, you don't want, you need to check if there's a zero first. If there's no zero, you don't want to go all through this. If there's no zero, then your code is good as is. So you need to have a check on zero first. Yeah. So anyway, let's push on. Okay, so find all the zeros, then you so actually it's better if we do check for zero. So how do you check if a list has zero? You do member queue. Okay, member queue curvature list 0. Okay, true. That means there is 0 in it. Yeah, so much problem, so much tediousness. So member queue curvature list 0. If this is true, then problem. Okay, if it's not true, then everything is simple. If it's not true, then we just do all this. Okay, then we just do all this. Okay, but if it's true, we got a problem, my friend. let's just return an empty list. Okay, let's just return empties and move this to here. Okay, so actually now this solves our problem because this code solves this problem, but actually it doesn't draw anything. We can try it. Okay, so evaluate quit kernel, quit local kernel, quit. Okay, then open this file. Where is it? Well, I don't understand why is it taking so long. Okay, select all, evaluate it. Good, close it, back to here, copy the code and put it here, paste it. If we run it, it's gonna be no error, but however it won't draw the thing. Oh, actually oh, we got some error here somewhere. Okay, I think that's it. I'm gonna walk offline. I need to take a break, and so that's it for today. Thank you guys for watching. It's like 2 hours and 20 minutes. Bye guys. Yeah, I gotta. So what is the error? Why is it private osculating circle? See you later. Latest told me. Yeah, actually, I know what is the problem. Because you don't. Yeah, you need to return. Actually, so let's return. because you are expected to return 3 things. Okay, so now let's try it again. Quit kernel local quit. Okay, then open this file. Yeah, it takes, why is it taking a while? Okay, select all, run it, close it, go back here, run it. Okay, that's it. Bye.